Last lecture on respiratory system and the control of respiration. As you can see in this picture, respiration is controlled by the medulla and the pons. There are two structures within the medulla, the dorsal respiratory group and the ventral respiratory group, seen here, dorsal and ventral. You can see the output from the dorsal respiratory group will go to the external intercostal muscles and the diaphragm for inspiration. It will also send output to the ventral respiratory group, and the ventral respiratory group will send signals to the accessory respiratory muscles for forced inspiration and to the external or internal intercostal muscles for forced expiration. Then in the pons, you also have two respiratory groups. You have the apneustic center and the pneumotaxic center. So we'll take a look at the function of those. The dorsal respiratory group is the main group for normal rhythm generation for breathing. It's similar in function to the SA node of the heart, so signals coming in through the vagus nerve and the glossopharyngeal nerve and the central chemoreceptors will let the dorsal respiratory group know what the levels of CO2 are, thus stimulating its depolarization and the firing of the neurons to send signals to the inspiratory muscles. During normal cellular respiration, we will breathe about 12 to 15 times a minute because that's how much CO2 is made. And CO2 is the primary stimulus for breathing rate, regardless of what we're doing, whether we're sleeping or just normally sitting or we're actively exercising. It's that rate of cellular respiration and the rate of CO2. And conversely, the rate of acid production or the drop in pH, that will also stimulate respiration. The second group within the medulla is the ventral respiratory group, which is active during forced ventilation, both inspiration and expiration. So signals from the DRG for forced inspiration and then expiration during stress and exercise. So the interaction between the DRG and VRG is very precise and gradual. So slow signals are going to pass from the DRG to the VRG and gradually increase to produce a smooth inspiratory effort instead of gasping. So when we're breathing rapidly, it's not always just a gasp. It's nice and smooth as we inhale and exhale. The pons then has the apneustic center and the pneumotaxic center again, and also receives chemo and mechanical receptor input as well as input from the higher brain centers, hypothalamus, during emotional events or fear, or just when we are wanting to hold our breath or if we're blowing up a balloon. So the apneustic center is for an inspiration, and the pneumotaxic center is going to send inhibitory signals to the inspiratory centers for expiration. And the pons respiratory group, PRG, of the apneustic and pneumotaxic centers, it helps adjust breathing rate and patterns while we sleep and exercise. So essentially, we have these interconnected neuronal networks in the medulla, and they inhibit and stimulate each other, so they cycle in their activity to generate rhythm. All right, so what really determines how rapidly we breathe and how deeply we breathe? The number one factor in determining rate of respiration and depth of respiration is CO2 levels. So CO2 most potent for influencing respiration. As CO2 levels rise, we get hypercapnia, and CO2 in the cerebrospinal fluid from the blood will decrease the pH through that same reaction that occurs in the red blood cells. So CO2 and water produce carbonic acid and then dissociates into hydrogen ions and bicarbonate. And the reason why why CO2 is so important if we're looking at a decrease in pH of our cerebrospinal fluid is that hydrogen ions don't cross the blood-brain barrier, but CO2 will. So as CO2 builds up in our bloodstream, gets to the environment of the brain, the CO2 will then diffuse into the cerebrospinal fluid, and then the pH will drop. So while rising CO2 levels begin the change in breathing rate, it's actually the regulation of the hydrogen ions, because the central chemoreceptors are stimulated by hydrogen ions and not CO2 levels. So it is the brain trying to get rid of hydrogen ions that drives breathing. But what produced those hydrogen ions in the first place? It was CO2. So in summary then, as the pH falls and CO2 rises, that will stimulate rapid breathing. When PCO2 levels are abnormally low, apnea may occur. And so if our pH was too high and our CO2 is too low, then that would stimulate breath holding. Because if there isn't enough CO2 to stimulate breathing, then we don't. There's a question that says, when a person hyperventilates, why do they experience a short feeling of apnea? So they don't have enough CO2. If you've been hyperventilating, you blow off too much CO2, and so then it stimulates you to hold your breath. Now, here's a little hint. If you want to hold your breath longer, so you have to dive under the water for a period of time or whatever, and you want to hold your breath even longer, hyperventilate first, blow off lots of CO2, and then you won't breathe as soon. I was going to say quickly, but you won't want to breathe as soon as if you didn't hyperventilate first. So think about also, what have you heard if a person's hyperventilating? What do we do to treat them? We have them breathe into a paper bag. So what does that do? Any of that extra CO2 that we're breathing out will collect in the paper bag, and then we'll breathe that back in again, and that will help restore CO2 levels back to normal. All right, so those that was the central chemoreceptors. Now if we take a look at the peripheral chemoreceptors that we have out in the carotid body and in the aortic arch, then they too will detect rising CO2 levels and then send signals through the vagus nerve and glossopharyngeal back to the DRG and say, you know what, guys, we better breathe a little faster. PO2 levels also will, falling PO2 levels will stimulate breathing, but not like we think. Normally we think, oh, I have to breathe because I don't have enough oxygen. No, I have to breathe because I have too much CO2. The only time I don't breathe because I don't have enough oxygen is if my pulmonary arterial PO2 is less than 60 millimeters of mercury. And we saw that in when we were taking a look at hemoglobin hanging on to oxygen, that it doesn't really want to let go of it until it gets below 60. And how often is arterial blood below 60? Not almost never, because the blood has been out in the lungs, comes back, goes to the aortic arch, and goes to the carotid sinus, and it should have a PO2 of 100. So rarely does the PO2 of our blood drop below 60 millimeters of mercury. So rarely does O2 stimulate breathing. Arterial pH, a drop in arterial pH also during times of exercise, for example, is going to cause a rise in ventilation. Try that sometime. Do something that's really anaerobic, like you're lifting weights, and see how long it takes you to start breathing heavily. The reason why you're breathing heavily in that particular case is because you're doing an anaerobic activity, you're generating a lot of lactic acid, and therefore you want to breathe. What else? So I got the exercise issue. High altitude. High altitude will also increase ventilation, but this time you breathe heavy because you don't have enough O2. Because you go up in higher elevations, especially if you're exerting yourself in higher elevations, your PO2 levels are going to be quite low, and compared to normal activity down at sea level. So that's why it's so important when hikers are climbing Everest anymore, that they have supplemental O2. And the problem with Everest today is that too many people that are too inexperienced, that are not mountaineers, are trying to climb this mountain just because they have $50,000 and an outfitter says, I'll get you to the mountain, to the top of the mountain and back down again. So people are like, it's a holiday, it's an eco holiday. It's not because we've been climbing our whole life and we want to get to the top. many people that climb Everest today are not trained for those high elevations, and therefore suffer high altitude pulmonary edema and cerebral edema, and many suffer greatly. And even some experienced mountaineers will die on Everest. We've had a couple this year that have passed away that have challenged all of the highest peaks on the 7 continents. So anyway, there's just a little extension of controlled respiration. Here is how that works. So if we take a look at the main things that influence, this is the main A number 1 right here, central chemoreceptors, high CO2, high hydrogen ions, or low pH, and will feed into the dorsal respiratory group and adjust breathing rate. The peripheral chemoreceptors will also have a positive stimulus on respiration, will increase respiration rate and depth. Receptors in muscles and joints, there's an idea that as we begin our exercise that there are signals that say, hey, look, we're starting to exercise, you better start breathing to get that oxygen down to us before we're just starving for it. So that will also have a positive stimulus on breathing. Other receptors, pain receptors, emotional stimuli, will either stimulate or inhibit respiration. Now, if you think about emotionally, what do? You hyperventilate. So that would be a positive, I don't know why, but that would be a positive stimulus for breathing. And then what do you do when you slam your finger in the door? Ooh, you hold your breath. And so there is the negative stimulus on, the inhibitory stimulus on breathing when you hurt yourself. And I don't know what the point of that is either, but it's what we do. Oh, while we're on this, this is where it would affect. There are some children, and maybe you've seen this happen before, where if they cry too much, they pass out. Okay, so that's a hyperventilation, emotional hyperventilation. Okay, so they're upset about something, they're crying, they hyperventilate, and then because of that thing I just told you about having apnea after crying or an emotional state, that hyperventilating, that they will actually pass out because of apnea, and they'll regain consciousness again. It's rather disconcerting when it's happening at the moment, but it's not gonna hurt them. I mean, we don't want that to happen to them, but and that's something that does. It's just like you can, if you have a child that says, I'm going to hold my breath till I die, well, that's never going to happen. We cannot voluntarily hold our breath, because these receptors over here are going to say, you know what, you're doing something stupid and we need to breathe again, so we are going to knock you out. So our higher brain centers, even though our diaphragm is a skeletal muscle and therefore we have control over that, either to stimulate it or inhibit it, our brain has the final say. I mean, our medulla, our reticular formation, has the final say. So I don't like what's happening here, and so you, cerebral cortex, can stop what you're doing. Okay, then we have some other things that are going to inhibit respiration, which we'll look at in a minute, but I'll just show you while they're on this picture. We have irritant receptors, pulmonary irritant receptors in the bronchi and the trachea. So when we get stuff in there, dust, whatever, things that we don't want, those receptors will then stimulate us to sneeze or cough. And then our stretch receptors in the lungs, if we are voluntarily inspiring, we don't want to overinflate the lungs, and so we're going to get to a stretch point where our lungs say, no, that's enough, and we won't be able to inhale anymore. It'll be the stop point of inhalation, and that's called the Herring-Breuer reflex, and we'll take a look at that in just a second. So here's pulmonary irritant reflexes. Communicate with respiratory centers via the vagus nerve. So whatever is in there, we just help get that out. And then here's the Herring-Breuer. So so there it is. Stretch receptors send those inhibitory signals to the medullary receptor centers to end respiration. Okay, and then like I said, the hypothalamus can send signals that either increase or decrease breathing rate, and then we can consciously do that too. And then here is just what happens when arterial PCO2 is too high and what we're going to do to counteract that. And then just one more little hit on this. So PCO2 levels, most important, influencing respiration. And there's that. So you can see those relationships. And then, like I said before, you have to have a PO2 less than 60 before you will breathe because of low CO2 or low O2. And then here's just the signals, how they travel through the vagus nerve and the glossopharyngeal nerve. And then again, arterial and exercise, high altitude, and stuff with chronic bronchitis and emphysema. And there it is. Okay, so that's it.